Look up at the night sky. What do you see? A scattering of bright points, familiar constellations, maybe the hazy band of the Milky Way if you're lucky. But here's the truth. What's visible to us is just a tiny fraction of what's really out there. The universe holds countless stars we'll never lay eyes on, not because they're too faint, but because they exist in ways that defy observation. Some vanish behind cosmic curtains of dust and gas. Others lurk in the voids between galaxies, drifting alone in eternal darkness. A few might even be hiding in plain sight, camouflaged by their own strange physics. Think about that for a moment. We live in an era where telescopes peer billions of light years into space, where probes venture beyond our solar system. And yet, there are stars so elusive, so enigmatic, they might as well be ghosts. Take the hypothetical dark stars, for example. These could be massive objects powered not by nuclear fusion, but by the annihilation of dark matter, glowing faintly in wavelengths our instruments can't easily detect. Or consider the runaway stars flung from their galaxies by violent collisions, now sailing through intergalactic space where no telescope will likely ever spot them. Even the stars we think we understand, like red dwarfs, might harbor bizarre secrets in their quiet, dim glow, their lifetimes stretching longer than the current age of the universe itself. This is the hidden symphony of the cosmos, stars that whisper instead of shine, that dance just beyond the edges of our perception, and that's what we're uncovering today. We're not just talking about distant points of light, we're exploring the universe's best-kept secrets, the stellar phenomena that challenge everything we thought we knew. From stars cloaked in black hole shadows to ones made of theoretical quark matter, these cosmic oddities redefine what's possible. So settle in. By the end of this journey, you'll never look at the night sky the same way again, because now you'll know what's lurking out there, unseen but undeniably real. Somewhere in the vast sprawl of the Andromeda galaxy, our closest cosmic neighbor, there could be a star so faint, so distant, that it slips through every observational net we've cast. Astronomers call it the Phantom Star, a ghostly presence hinted at by subtle anomalies in the galaxy's outer reaches. The problem, it's not just far away, it's invisible by conventional means. Light from this star, if it exists, is stretched thin across 2.5 million light-years, diluted to near nothingness by the time it reaches us. But here's where the universe's own tricks might help us catch it. Gravitational lensing, a phenomenon where massive objects bend space-time, magnifying the light of objects behind them, could be the key. Imagine a cosmic magnifying glass warping the fabric of reality itself, amplifying whispers of light we'd otherwise never detect. If a dense cluster of galaxies aligns just right between us and Andromeda, it might distort space in a way that briefly illuminates the Phantom Star, like sunlight glinting off a hidden coin. We've seen this happen before. Distant supernova, once invisible, suddenly flaring into view because of lensing. The same physics could reveal Andromeda's shyest resident. But there's a catch. This star wouldn't just be dim. It might belong to a class of ultra-cool, ancient stars that burn so slowly, their glow is barely a flicker against the cosmic backdrop. Picture a campfire ember compared to a spotlight, except this ember has been smoldering for billions of years, untouched by telescopes. Or worse, it could be veiled by interstellar dust, its light swallowed before it ever reaches the edges of its own galaxy. Yet the hunt continues. Every time astronomers map Andromeda's halo of rogue stars or study microlensing events, they're piecing together clues to this stellar phantom's existence. What makes this search so thrilling isn't just the star itself, it's what it represents. Finding it would confirm that even in a galaxy we've studied for centuries, secrets lurk in the shadows. It's a reminder that the universe doesn't reveal its mysteries easily, and sometimes the most profound discoveries begin as whispers in the dark. Deep in the heart of our galaxy, where the supermassive black hole Sagittarius a star reigns, there might be a star trapped in an unthinkable dance, one so violent and extreme that it defies everything we know about survival. This isn't just any stellar companion. It's a cosmic gladiator whipping around the black hole's event horizon at nearly a third the speed of light, all while being cloaked from view by the black hole's swirling, superheated accretion disk. We can't see it directly, but the universe leaves us clues in the ripples of spacetime itself. Gravitational waves, the faint tremors in the fabric of reality caused by massive objects accelerating, betray this star's existence. Every close pass it makes around the black hole sends shudders through space-time, like a tuning fork struck against the edge of the cosmos. Advanced detectors like LIGO and Virgo have glimpsed these disturbances, but here's what's chilling. The signals don't match a black hole alone. There's something else out there, something massive enough to warp spacetime but invisible to our telescopes. That missing piece, a star locked in a death spiral, its light swallowed by the black hole's glare. What makes this scenario even more astonishing is how the star endures. Most objects venturing this close to a black hole would be shredded into a stream of plasma, a process called spaghettification. Yet somehow this star persists. Maybe it's a compact, ultra-dense neutron star, its incredible gravity holding it together against the tidal forces. Or perhaps it's a rogue stellar remnant flung into this orbit by some ancient galactic collision. Either way, it's surviving conditions that should be impossible, leaving behind a trail of gravitational breadcrumbs for us to follow. The implications are staggering. If confirmed, this hidden companion would be the ultimate test of Einstein's theory of relativity, pushing the boundaries of how matter behaves under extreme gravity. It could also rewrite our understanding of black hole environments, not as sterile voids, but as dynamic arenas where stars wage a desperate battle against annihilation. And here's the haunting part: we may never see it directly. The accretion disk's blinding glow ensures this star remains a phantom, its presence known only through the whispers of warped spacetime. But that's the beauty of cosmic detective work. Sometimes the universe's greatest secrets aren't found in the light we see, but in the invisible forces bending the very framework of existence. This star, if it's truly there, isn't just hiding, it's teaching us to listen to the cosmos in a whole new way. In the constellation of Cygnus, astronomers once tracked a monster, a hypergiant star named N39, one of the most massive stars ever recorded. Then one day it simply vanished, no explosion, no dramatic supernova farewell, just an eerie absence where a star 25 times heavier than our sun had once blazed. This wasn't a case of bad data or a telescope error. The star had been under observation for years, its colossal brightness unmistakable. Yet when researchers pointed the Hubble Space Telescope back at its coordinates in 2019, they found only darkness. It was as if the universe had reached out and plucked a star from existence. This disappearance throws a wrench into everything we thought we knew about how massive stars die. Normally, a hypergiant this size would go out in a cataclysmic supernova, leaving behind a neutron star or black hole. But N39 skipped the fireworks entirely. The leading theory, it underwent a phenomenon called direct collapse, where a star's core becomes so dense and massive that it implodes straight into a black hole, swallowing the rest of the star from the inside out. No explosion, no warning, just a silent, voracious exit. If confirmed, this changes the game for stellar evolution. Direct collapse was once thought to be vanishingly rare, but N39 suggests it might happen more often than we realized. That means there could be black holes lurking in our galaxy, former hypergiants that slipped away unnoticed, their deaths too quiet to detect. It also implies that some of the universe's heaviest stars might leave no chemical legacy behind. Supernovas scatter elements like iron and gold across space, seeding future stars and planets. But a star that vanishes, it takes those materials with it, robbing the cosmos of the building blocks for new worlds. Here's where it gets even stranger. The Very Large Telescope in Chile later detected a faint infrared glow near N39's last known location, a possible signature of dust heated by a newborn black hole's accretion disk. If true, this ghostly afterglow would be the only tombstone a star like this leaves behind. No grand explosion, no luminous remnant, just a whisper of warmth in the void. What's thrilling and humbling about this mystery is how it forces us to rethink the life cycles of the universe's most extreme objects. Stars aren't just points of light, they're stories written in plasma and gravity. And sometimes the most compelling chapters are the ones that end in silence. Now, let's venture into one of the universe's most perplexing possibilities, a star that shouldn't exist, at least not by the rules we know. Imagine a celestial object so alien it doesn't shine, doesn't emit heat, and doesn't even interact with light. This isn't science fiction. It's the dark matter star, a hypothetical giant lurking in the cosmic shadows, made entirely of the universe's most elusive substance. Dark matter makes up roughly 85% of all matter in the cosmos, yet we've never directly observed it. It doesn't absorb, reflect, or emit electromagnetic radiation, meaning our telescopes are blind to it. But what if this mysterious material could clump together under its own gravity, forming structures as vast and complex as stars? Theoretically, under just the right conditions, dark matter particles could annihilate upon collision, releasing enough energy to create a stable, self-sustaining object. Unlike normal stars powered by nuclear fusion, dark matter stars would glow faintly with gamma rays, their cores churning with invisible activity. The catch: we'd never see one directly. Their detection would rely entirely on subtle gravitational fingerprints tugging on nearby stars, bending light around them like cosmic mirages, or distorting the fabric of spacetime itself. In fact, astronomers might have already stumbled upon clues. Some regions of space exhibit gravitational anomalies too pronounced for the visible matter present, as if unseen giants are hiding in plain sight. Take the galaxy cluster Abell 521, where the gravity of an entire group of galaxies doesn't match the glow of their stars. Could a swarm of dark matter stars be lurking there, anchoring the cluster with their invisible mass? Even stranger, these phantom stars might solve another cosmic riddle, the mystery of early supermassive black holes. Some of these behemoths appear in the infant universe, far too soon to have grown from ordinary stellar collapses. But if dark matter stars existed, their sheer density could have collapsed directly into black holes, seeding the cosmos with monsters before the first conventional stars even ignited. The implications are staggering. If dark matter stars are real, they'd rewrite the story of how structures form in the universe, offering a hidden scaffold for galaxies we thought we understood. They'd also force us to confront a humbling truth. The cosmos might be filled with entire categories of objects we've never dreamed of, invisible architects shaping the night sky from the shadows. And that's the real thrill of astronomy, not just mapping what we can see, but daring to imagine what we can't. Picture a star torn from its home, not just wandering between planets, but flung entirely outside its galaxy, adrift in the unimaginable emptiness between cosmic islands. This is the fate of a rogue star, a solitary exile hurled into intergalactic space by violent galactic collisions, or the gravitational slingshot of a supermassive black hole. Unlike stars hidden behind dust or cloaked by exotic physics, this one is invisible for a simpler yet equally haunting reason. It's drowning in darkness with no galaxy's glow to backlight it, no neighboring stars to betray its presence. Most stars live in communities, whether in spiral arms or globular clusters, their light mingling to create the glittering tapestries we see through telescopes. But a rogue star has no such company. It travels alone through a desert millions of light years wide, where the nearest galaxy might be as distant as Earth is from the center of the Milky Way. Even if it's a luminous giant, its light spreads thinly across the void, reaching us as little more than a phantom flicker. if it reaches us at all. Spotting one would be like trying to see a single match flame from across an ocean. Yet their isolation makes them cosmic time capsules, untouched by the turbulent gas and radiation of a galaxy. These stars preserve the pristine chemistry of their birthplaces. Imagine a stellar archaeologist's dream, a relic from the early universe, its composition unaltered by billions of years of galactic pollution. Some might even be first-generation stars, forged from pure hydrogen and helium in the aftermath of the Big Bang. But here's the cruel irony: the very purity that makes them invaluable also makes them nearly undetectable. Without heavier elements to absorb and re-emit light, their spectra fade into the background noise of the cosmos. Astronomers hunt them indirectly, using statistical anomalies or the rare gravitational lensing event that briefly magnifies their faint light. In 2018, a team using the Keck Observatory spotted a candidate rogue star in the Virgo cluster, a red giant drifting so far from any galaxy that its motion suggested an ancient ejection. Then there's the mysterious dark free-floating planet population, which might include stars too dim to classify. Could some of these actually be rogue stars, their nuclear fires long since dead, cooling into pitch-black cinders? What's chilling is the scale of what we're missing. Simulations suggest that up to half of all stars might live outside galaxies, banished to the intergalactic wilds. That means the night sky we admire, the Milky Way's shimmering band, Andromeda's soft glow, could be just the visible fraction of a far lonelier universe. Every patch of empty black between galaxies might hide untold numbers of these wanderers, their stories written in light we'll never see. Somewhere in the depths of the cosmos spins a silent predator, a neutron star so still, so undetectable, that it defies the very definition of its kind. We call them neutron stars, the collapsed cores of dead stars, typically known for their lighthouse-like beams of radiation. But this one, it broadcasts nothing. No rhythmic pulses, no sweeping radio waves, just the cold, dark certainty of its gravity, warping space around it like an unseen hand pressing down on fabric. Neutron stars are already extreme by nature. A teaspoon of their material would weigh 1 billion tons on Earth. Most reveal themselves as pulsars, spinning rapidly and emitting beams of radiation from their magnetic poles. When those beams sweep across Earth, our telescopes detect regular pulses like cosmic metronomes. But take away those beams and you're left with something far more elusive, a dead pulsar, or what scientists call a radio-quiet neutron star. Without its telltale pulses, it becomes nearly invisible to traditional radio telescopes, slipping through our observational nets. Yet these silent giants might still betray their presence in other ways. X-ray telescopes could be the key. When neutron stars accrete material from a companion star or interstellar gas, the infalling matter heats to millions of degrees, glowing fiercely in X-rays. Picture a cosmic forge where space itself ripples with energy too intense for human eyes to see, but bright as a supernova to instruments like Chandra or XMM Newton. Some of the darkest, most isolated neutron stars might only reveal themselves this way through the faint X-ray whisper of matter spiraling into their unfathomable gravity. There's also the curvature of spacetime to consider. A neutron star's gravity is so intense that it bends light passing nearby, an effect called microlensing. If one drifted in front of a distant star, the background star's light would temporarily brighten, not because the neutron star emits anything, but because its mass acts like a lens. Astronomers have used this technique to spot rogue planets and black holes. Could the same method uncover these invisible stellar corpses? The implications are profound. If neutron stars can hide this effectively, how many might be lurking in our galaxy undetected? Current estimates suggest there could be over 1 billion neutron stars in the Milky Way, yet we've only catalogued a tiny fraction. The rest might be these radio-silent phantoms, their presence known only by the subtle warping of space or the occasional X-ray flicker. What's captivating about this mystery isn't just the challenge of detection, it's how these objects force us to rethink the boundaries of visibility in the universe. Light and radio waves are only part of the story. To truly map the cosmos, we must learn to see with gravity, with X-rays, with the distortions of space-time itself. And somewhere out there, spinning in perfect silence, these neutron stars are waiting not to be seen, but to be discovered. Between the blazing stars and the frozen planets lies a cosmic misfit, too massive to be a planet, yet too small to truly shine. These are brown dwarfs, the universe's ghostly in-betweeners, lurking in the darkness like forgotten embers. They form just like stars, collapsing from vast clouds of gas, but they never gather enough mass to ignite the nuclear fusion that powers their larger cousins. Instead, they hover in a twilight state, radiating only a faint infrared glow as they cool slowly over billions of years. What makes them so elusive? Their dimness is only part of the story. Many brown dwarfs drift alone through interstellar space, untethered to any star system, making them nearly invisible against the black backdrop of the cosmos. Even our most powerful telescopes struggle to spot them unless we know exactly where to look. Recent advances in infrared astronomy, though, have begun pulling these phantoms into the light. Take WISE 0855, for example. Discovered in 2014 by NASA WISE telescope, this brown dwarf floats just 7.4 light-years away, yet its temperature hovers at a frigid -10 degrees Fahrenheit, colder than an Arctic winter. Its faint heat signature is barely distinguishable from the cosmic microwave background, the afterglow of the Big Bang itself. But the real shock came when astronomers realized some brown dwarfs might be far older than we thought. In 2021, the Hubble Space Telescope identified a population of these objects in the globular cluster NGC 6139, ancient relics dating back over 10 billion years. These primordial brown dwarfs challenge our understanding of star formation in the early universe, suggesting that failed stars might have been far more common than we ever imagined. Even stranger, some brown dwarfs defy classification entirely. Objects like those found in the TRAPPIST-1 system blur the line between planet and star, with atmospheres swirling with molten iron clouds and storms that would dwarf Jupiter's Great Red Spot. Others, like the mysterious rogue brown dwarf SIMP 0136, exhibit magnetic fields so powerful they generate auroras visible in radio waves, a haunting light show with no star to call home. The more we uncover, the clearer it becomes. Brown dwarfs aren't just celestial curiosities. They're a hidden population, a shadowy network of objects that might outnumber visible stars in our galaxy. And as our telescopes grow more sensitive, we're peeling back the darkness to reveal a universe far richer and far stranger than we ever dreamed. Somewhere in the Orion Nebula, a star is being born, but you'd never know it by looking. Thick curtains of cosmic dust, hundreds of light-years wide, shroud it from view, absorbing every shred of visible light before it can reach our telescopes. This isn't just any dust. These are molecular clouds so dense they could swallow entire solar systems whole, their particles finer than smoke yet packed tight enough to blot out stars like a cosmic eclipse. To the naked eye, or even Hubble's keen vision, this region appears as nothing more than a dark splotch against the nebula's glow, but switch to infrared and the universe pulls back the veil. Infrared light, with its longer wavelengths, slips between dust particles like a ghost passing through walls. Where visible light gets absorbed, infrared radiation, emitted by the star's heat, travels unimpeded, carrying secrets to our telescopes. NASA James Webb Space Telescope has turned this technique into an art form. Its piercing infrared gaze reveals nurseries of newborn stars cocooned in these dusty wombs, their fiery cores glowing bright in wavelengths our eyes can't see. One standout is the protostar HOPS 383, buried so deep in the Orion molecular cloud complex that its visible light is reduced to a billionth of its original brightness. Yet in infrared, it blazes like a beacon, surrounded by swirling disks of gas that may one day form planets. What's astonishing isn't just our ability to peer through the dust, it's what we find when we do. These hidden stars often defy expectations. Take the case of the Black Widow pulsar, a neutron star shrouded in dust so thick it was only detected when its high-energy gamma rays punched through the haze. Or the enigmatic object G0.25 plus 0.06, lurking behind the Milky Way's central dust lanes. Until recently, astronomers assumed it was just another patch of darkness. Then infrared observations revealed a monstrous young star, 30 times the Sun's mass, throwing off enough ultraviolet radiation to ionize the surrounding cloud, a powerhouse hidden in plain sight. The implications ripple far beyond mere curiosity. Stars like these are cosmic chemists, forging heavy elements and scattering them across galaxies. By studying them through their infrared fingerprints, we're rewriting the story of stellar birth. Some of these dust-cloaked giants might even be the elusive, missing population 3 stars, the universe's first generation, thought to have formed from pure hydrogen and helium. If any still exist, they're likely veiled by eons of accumulated cosmic debris, their light stretched into the infrared by the expansion of the universe itself. Yet the challenge remains. Even infrared has its limits. The densest dust clouds, like those in the Bok globules drifting between stars, can dim even long-wavelength light to near nothingness. To uncover their secrets, astronomers now combine infrared with radio telescopes, mapping molecular emissions like carbon monoxide that trace the outlines of hidden stellar cradles. It's a reminder that the cosmos guards its mysteries jealously, revealing them only to those who learn to see in every wavelength at once. And somewhere in those dark recesses, countless more stars wait, their stories whispered not in light but in the silent warmth of dust-shrouded birth. At the edge of the observable universe, where light takes billions of years to reach us, there's a cosmic lighthouse so bright it defies comprehension, a quasar. From afar, it looks like a single dazzling star, but zoom in, and you'll find something far more extraordinary. An entire galaxy's worth of light being vomited into space by a supermassive black hole's insatiable appetite. Yet buried beneath that blinding glare lies the quasar's best-kept secret, its hidden stellar engine, a star-like core fighting to be noticed against the most luminous object in existence. Quasars shine with the power of 1,000 Milky Ways, their brilliance fueled by gas spiraling into black holes weighing billions of suns. But what often gets lost in that spectacle is the star-forming frenzy happening in their shadows. At the heart of many quasars, astronomers suspect a dense cluster of newborn stars, some forming at rates hundreds of times faster than in our galaxy, packed so tightly around the black hole that their collective glow gets drowned out by the surrounding chaos. Imagine trying to spot a candle lit in front of a searchlight. That's the challenge of finding these stellar powerhouses. The key to uncovering them lies in the quasar's hidden fingerprints. When scientists analyzed the infrared spectra of distant quasars like APM 08279 plus 5255, they found unexpected dips and peaks in the light signatures of heavy elements typically forged in stars. These clues suggest something astonishing. Even as the black hole devours everything around it, stars are being born in the maelstrom, their nuclear furnaces churning out elements that shouldn't exist in pure quasar light. Some might even orbit so close to the black hole that they complete a full revolution in mere hours, skating along the edge of oblivion. But here's the twist: quasars don't just mask these stars, they might need them. The same violent collisions and shock waves that rip gas clouds apart in the black hole's vicinity also compress them, triggering runaway star formation. These stars, in turn, could feed the quasar, their stellar winds and explosive death supplying fresh fuel for the black hole's next meal. It's a self-sustaining cycle of creation and destruction playing out on a scale we can barely fathom. What's truly humbling is the raw power imbalance. The brightest quasar known, SDSS J0100 plus 2802, outshines our Sun by 400 trillion times. Against that backdrop, even the most massive stars are mere fireflies, yet without them the quasar might flicker and fade. They're the invisible workforce behind the universe's most dazzling spectacle, proof that sometimes the most important players aren't the ones in the spotlight. There's a star orbiting so close to the Milky Way's central black hole that time itself seems to stop for it. From our vantage point, its light stretches into an infinite red smear, its motion slowing to a crawl as if the universe has hit pause. This isn't science fiction, it's the mind-bending reality of time dilation, one of Einstein's most startling predictions. The closer an object gets to a black hole's event horizon, the more space-time warps, stretching seconds into years for anyone watching from afar. For this star, every orbit it completes might take mere hours from its own perspective, but to us, that same journey could appear to last centuries. The star in question, known as S2, skirts just 17 light hours from Sagittarius, a star, our galaxy's supermassive black hole. At that distance, the tug of gravity is so fierce that the star's light loses energy fighting its way out, shifting toward the red end of the spectrum in a phenomenon called gravitational redshift. But the real magic happens when you consider time. Einstein's theory of relativity dictates that clocks tick slower in stronger gravitational fields. For S2, this means time passes noticeably slower compared to Earth. If you could stand on its surface, assuming you survived the tidal forces, you'd age far slower than everyone back home, a real-life twist on interstellar time travel. Yet the most haunting implication isn't just the star's slowed clock. It's the possibility of a star crossing the point of no return. Imagine a star edging so close to the event horizon that its light takes years, then millennia, then eons to reach us. From Earth, its final moments would appear frozen, its last flicker of light suspended in time forever. Astronomers call this photon starvation, the star's image fading not because it's gone dark, but because its photons are stretched so thin across space-time that they arrive as mere whispers. The star could already be shredded by tidal forces, yet its ghostly afterimage would linger in our sky, a cosmic hologram of its demise. This extreme environment also offers a rare test of relativity. S2's orbit isn't a perfect ellipse like planets around the Sun. It traces a rosette-shaped path, its perihelion shifting slightly with each revolution, a wobble predicted by Einstein over a century ago. In 2018, the gravity instrument at the Very Large Telescope confirmed this Schwarzschild precession with stunning precision, proving that even in the most chaotic corners of the galaxy, Einstein's equations hold sway. What's humbling is how this star bridges the theoretical and the tangible. Time dilation isn't just a quirk of math, it's etched into the motion of a real object visible through our telescopes. And somewhere out there, other stars might be orbiting even closer, their time so dilated that they've effectively vanished from our observable universe, their existence known only by the subtle ripples they leave in space-time. They're not just hidden, they're unfolding in a different timeline altogether, a reminder that the cosmos operates by rules far stranger than fiction. Long before galaxies spiraled into shape, before planets formed or life stirred, the universe flickered to life with its very first stars, behemoths unlike anything we see today. These were the population 3 stars, pure and primal, forged exclusively from hydrogen and helium left behind by the Big Bang. With no heavy elements to weigh them down, no dust to temper their brilliance, they burned ferociously, hundreds of times more massive than our Sun, their lives measured in millions rather than billions of years. Their deaths seeded the cosmos with the first heavy elements, yet their light might still be reaching us, stretched and dimmed by the expanding universe into near invisibility. Detecting these ancient giants is like trying to spot a campfire from across the Atlantic. Their light, emitted over 13 billion years ago, has been redshifted. pulled by cosmic expansion into the infrared, far beyond what the human eye can perceive. Even our most advanced telescopes strain to catch whispers of their existence. But in 2022, the James Webb Space Telescope may have glimpsed a ghostly contender, a distant galaxy called Glass Z13, whose peculiar light signature hints at stars devoid of metals, a telltale sign of population 3 survivors. The evidence is thin, a faint smudge in the data, but the implications are staggering. If confirmed, it would be like uncovering a living fossil from the dawn of time. What makes these stars so alien isn't just their age, it's how they lived. Without carbon, oxygen, or iron to regulate their nuclear reactions, they convulsed in violent, unstable bursts, their cores reaching temperatures extreme enough to fuse elements in ways modern stars never could. Some might have collapsed directly into black holes, skipping the supernova stage entirely, while others could have exploded as pair instability supernova cataclysms so powerful they vaporized themselves completely, leaving no remnant behind. Yet their legacy is everywhere. Every atom of gold in your jewelry, every breath of oxygen you take, traces back to these primordial furnaces. They were the universe's first alchemists, transforming the simplicity of hydrogen into the complexity that would eventually build planets, oceans, and us. And here's the haunting part: their light might still be en route. Somewhere in the void, photons emitted by long-dead population 3 stars could be nearing Earth, carrying stories from a time when the cosmos was young, dark, and utterly unrecognizable. The next generation of telescopes won't just search for these stars, they'll be time machines, peering back to an era when the first lights flickered on in the eternal night. There's a star hidden inside what should be its own funeral shroud, a planetary nebula so thick with expelled gas and dust that the star itself has vanished from view. These glowing clouds, often mistaken for remnants of dead stars, are actually the outer layers of a dying sun, cast off in its final act, but occasionally the star at their heart doesn't fade quietly. Instead, it becomes trapped inside its own creation, its light scattered and absorbed by the very material it once ejected. Take the iconic Ring Nebula, for example. To the casual observer, it's a beautiful smoke ring-like structure floating in space, but deep inside that ring, obscured by curtains of ionized gas, lies a white dwarf star, the nebula's progenitor. Its light, once fierce enough to illuminate the nebula, is now so diffused by the surrounding gas that only the most sensitive instruments can pick out its faint glow. The nebula isn't just hiding the star, it's filtering it, bending and redirecting its light like a cosmic prism. So how do astronomers spot these buried stars? The answer lies in decoding the nebula's own light. Planetary nebulae glow because their gas is energized by ultraviolet radiation from the hidden star. By analyzing the wavelengths of that glow, specifically the way certain elements like oxygen and nitrogen emit light, scientists can work backward to deduce the star's temperature, size, and even its chemical composition. It's like listening to an echo to understand the shape of the room it bounced off. Some of these stars leave even subtler clues. In the case of the Southern Crab Nebula, the central star isn't just obscured, it's locked in a violent dance with a companion, its flares of energy punching through the nebula in erratic bursts. These flares create shock waves in the surrounding gas, visible as ripples in the nebula's structure when observed with radio telescopes. Other stars, like the one inside the Calabash Nebula, spew out jets of material at supersonic speeds, carving intricate tunnels in the surrounding cloud that betray their presence. The most haunting examples, though, are the ones where the star has faded so completely that it's only detectable by its gravitational influence. The nebula might still expand, its outer edges drifting outward, but without the star's radiation to excite the gas, the glow dims to near nothingness. In these cases, astronomers rely on the nebula's motion, the way its knots and filaments shift over decades, to trace the unseen tug of the star at its core. What makes these hidden stars so captivating isn't just the challenge of finding them. It's the irony. A star's death throes create a monument so grand, it erases the very thing that built it. And somewhere in that glowing haze, the star lingers, not dead, not alive, but suspended in a twilight where light and shadow merge into something stranger than either. Deep in the constellation Cygnus, two stars orbit one another in a silent dance, but only one is visible. The system known as Cygnus X1 has puzzled astronomers for decades, not because of what we see, but because of what we don't. The visible star, a blue supergiant 30 times the mass of our Sun, twists and wobbles as if tugged by an unseen hand. Its erratic motion betrays the presence of something dark, something massive, a companion so dense that not even light can escape its grip. This isn't just a hidden star, it's a black hole lurking in the binary's shadow, its existence revealed only through gravity's inexorable pull. How do you find a star that emits nothing? The answer lies in the visible star's tortured orbit. Imagine tying a ball to a string and swinging it in circles. Now replace the string with an invisible force, and you've got Cygnus X1. The blue supergiant's path isn't smooth. It speeds up, slows down, and even shifts position slightly over time, all clues pointing to an unseen mass warping its trajectory. By measuring these minute deviations, astronomers calculated the invisible object's weight around 15 solar masses, far too heavy to be a neutron star or white dwarf. The only explanation, a black hole feeding silently on its companion stellar winds. But black holes aren't the only dark twins in binary systems. Take Sirius, the brightest star in Earth's night sky. For over a century, astronomers noticed its path wasn't a straight line but a gentle zigzag, as if swaying to an unheard rhythm. The culprit, Sirius B, a white dwarf so faint it wasn't spotted until 1862. Though smaller than Earth, this stellar corpse packs the Sun's worth of mass into a smoldering ember no hotter than a dim light bulb. Its gravity yanks Sirius back and forth like a cosmic pendulum, proving that even in death, stars can dictate the dance. The real marvel is how these dark twins reshape our understanding of stellar partnerships. In systems like V404 Cygni, the visible star's light dims unpredictably, not because the companion eclipses it, but because the black hole's gravity bends the light like a funhouse mirror, warping our view from Earth. Other binaries, like Epsilon Aurigae, hide their secrets behind thick disks of dust, their companions glimpsed only when the veil thins every 27 years. These systems force us to rethink what a star even means. Is it something that shines, or is it anything with enough gravity to rewrite the rules of its corner of the cosmos? What's humbling is how often the universe hides its most fascinating players in plain sight. For every black hole or white dwarf we detect, there could be dozens more, their presence etched not in light but in the subtle tremors of the stars they orbit. They're cosmic ventriloquists throwing their voices through gravity, leaving us to decipher the echoes. And as our telescopes grow sharper, we're learning to listen not just with our eyes, but with the laws of physics themselves. Somewhere beyond the edges of our cosmos, past the farthest galaxies, the last whispers of the cosmic microwave background, the voids where even dark matter thins to nothing, there might be another universe entirely. And in that universe, stars burn under different laws of physics, their light painting skies no human eye will ever witness. This isn't just science fiction. It's a possibility rooted in multiverse theory, the idea that our universe is one bubble among countless others in an infinite cosmic foam. If true, then somewhere in that vast ensemble, stars exist that defy everything we know, some with extra dimensions folded into their cores, others shimmering in wavelengths outside our spectrum, or even powered by forces we've yet to discover. Think about what that means for a moment. In one universe, stars might fuse elements we've never imagined, their cores threaded with exotic particles that stabilize them for trillions of years. In another, gravity could operate differently, allowing stars to grow so massive they dwarf our supermassive black holes, yet remain stable under their own weight. There might even be universes where stars don't form at all, where matter clumps into bizarre, luminous structures that aren't quite stars, aren't quite galaxies, but something entirely other. The variations are as limitless as the multiverse itself. The wildest part, these aren't just thought experiments. Cosmic inflation theory suggests that during the Big Bang, space-time expanded so rapidly that pockets of it pinched off into separate universes, each with its own physical constants. Some of those universes could harbor stars made of strange matter quarks rearranged into configurations impossible in our reality. Others might have stars that pulse in and out of existence, blinking between dimensions. And because these universes are causally disconnected from ours, their light will never reach us, their physics never leave a trace in our telescopes. They're the ultimate hidden stars, locked away behind the one barrier even science can't breach, the edge of reality itself. Yet here's where the speculation gets thrilling. If the multiverse is real, and if some of these alternate universes bump against ours in higher dimensional space, they might leave faint imprints in our cosmos. Some physicists hunt for these fingerprints in the cosmic microwave background, searching for anomalous patterns, bruises from a collision with another universe long ago. Others suggest that dark energy, the mysterious force accelerating our universe's expansion, could be the gravitational tug of a neighboring universe bleeding through the void. If so, then the light of those alien stars isn't just a phantom, it's a shadow warping the fabric of our own existence. What's humbling is how this reshapes the meaning of hidden. The stars we've explored so far in this video are concealed by dust, distance, or exotic physics, but they're still of our universe. These parallel stars are something else entirely. They're reminders that the cosmos might be vaster and stranger than we ever dared to dream, with whole constellations forever beyond our reach, their stories written in a language we'll never learn. And that's the most beautiful paradox of all. The more we uncover about our universe, the more we realize how much lies quite literally outside it. The Milky Way's heart is a crowded, chaotic place, a superdense core crammed with hundreds of billions of stars, their combined glow forming the galaxy's signature bulge. But what we see is just the surface. Behind that golden haze lies an entire hidden population of stars, swallowed by the sheer density of the galactic center. Picture sunlight filtered through thick fog. Only here, the fog is a relentless sea of stars, gas, and dust, each layer absorbing and scattering light until individual objects vanish into the background glow. Peering through this stellar thicket is one of astronomy's greatest challenges. The Milky Way's central bulge spans thousands of light years, with stars packed so tightly that their combined gravity warps spacetime itself. To uncover what's hidden, astronomers have to think like cosmic detectives. Infrared telescopes are their best tool. Light at these longer wavelengths slips through dust clouds that block visible light, revealing stars otherwise invisible. NASA's Spitzer Space Telescope mapped thousands of these cloaked giants, including ancient red giants and mysterious variables that pulse unpredictably. But even infrared has limits. The very center of the galaxy is so crowded that stars overlap in telescope images, their light blending into an unresolved blur. Here, scientists turn to a technique called adaptive optics, which uses lasers to correct for Earth's atmospheric distortion, sharpening the view. The Keck Observatory in Hawaii employs this method to pick out individual stars just light days from Sagittarius A star, our galaxy's supermassive black hole. Some of these stars orbit at breakneck speeds, their paths tracing the black hole's overwhelming gravity, yet they'd remain invisible without these high-tech corrections. The most exciting discoveries come from combining multiple wavelengths. Radio telescopes like ALMA pierce through the densest gas clouds, detecting molecules like carbon monoxide that trace hidden star-forming regions. Meanwhile, X-ray observatories spot young, massive stars by the fierce radiation they emit. Together, these tools reveal a bustling stellar metropolis, newborn stars still wrapped in dusty cocoons, aging red giants exhaling vast planetary nebulae, and runaway stars flung outward by gravitational encounters. Perhaps the greatest surprise is how many stars defy expectations. The bulge was once thought to be a quiet retirement home for ancient stars, but we now know it's a dynamic factory where stars form in chaotic bursts, triggered by gas clouds colliding near the black hole. Some of these stars might even be interlopers stolen from dwarf galaxies torn apart by the Milky Way's gravity, their origins erased by time. Every new observation peels back another layer, proving that even in our own galactic backyard, the universe keeps its secrets close. In the vast celestial catalogue, there's an entry that once baffled astronomers: a star that burned too bright, too far away, with a light that didn't quite match anything else in the sky. Catalogued as SDSSJ0140+2344, this point of light was initially logged as just another distant sun. But when researchers trained the Sloan Digital Sky Survey on it, the truth came crashing down. This wasn't a star at all. It was a quasar, a galaxy's core so violently energetic it outshone its host by 1,000 times, its light traveling 7 billion years to reach us. The mistake was understandable. Through early telescopes, quasars and stars looked identical, tiny, bright pinpricks. Only when spectroscopy split their light into rainbows did the differences scream for attention. The quasar's spectrum revealed lines shifted far into the red, a hallmark of cosmic distances no single star could ever span. Worse, its light bore the fingerprints of elements like magnesium and iron, forged not in a star's core but in the maelstrom around a supermassive black hole. This was no stellar object, it was a galactic engine, a beast millions of times our sun's mass, devouring matter so fast it blazed with the brightness of 1 trillion suns. The misclassification wasn't just an error, it was a glimpse into how much we had to learn about the universe's extremes. Quasars weren't the only imposters. In the early 20th century, the spiral nebula Andromeda was debated as a nearby star cloud, until Edwin Hubble spotted Cepheid variable stars within it, proving it was a separate galaxy. Then there's the case of the Green Star, an object in the Large Magellanic Cloud that turned out to be a supernova remnant, its eerie glow coming from ionized oxygen rather than stellar fusion. Each correction rewrote the celestial map, reminding us that the cosmos is full of actors playing roles they weren't born for. Modern telescopes have made such mistakes rarer, but the universe still loves a good deception. The Gaia spacecraft, mapping 1 billion stars, occasionally flags an object with unusual motion, only for follow-ups to reveal it's a distant quasar, mimicking a nearby star's parallax. Even gravitational lensing can warp a galaxy's light into a faux stellar point, as happened with the Einstein cross, where one quasar appears as 4, only revealed its true nature when Hubble's sharp eye resolved the illusion. The lesson here isn't just about flawed data, it's about the universe's endless creativity. A flicker of light might be a dying ember in our backyard or a galactic inferno halfway across existence. And with every technological leap, we peel back another layer of cosmic camouflage, finding new ways the heavens hide their greatest spectacles in plain sight. There's a cruel irony in the cosmos, a star so radiant, its brilliance becomes its own cloak. Meet Vega, one of the brightest stars in our night sky, blazing with such intensity that its glare drowns out the finer details astronomers crave. Telescopes pointed at Vega don't just see a star, they see a supernova-like burst of light, its glare smearing across lenses and sensors, obscuring the very features scientists want to study. This isn't just a technical nuisance, it's like trying to read a book while someone shines a floodlight in your eyes. The solution, a coronagraph, a device originally designed to study the sun's faint corona by blocking its overwhelming disk. Adapted for stars like Vega, it works like a cosmic visor, placing a physical mask inside the telescope to block the star's direct light. Think of it as cupping your hands around your eyes to spot a firefly near a street lamp. By suppressing Vega's glare, astronomers can finally glimpse the subtle structures around a debris disk's potential planets, even asymmetries in its atmosphere that hint at violent magnetic activity. But coronagraphs aren't perfect. Vega's light is so fierce it scatters inside the telescope itself, creating ghostly halos that can mimic planetary signals. To combat this, modern instruments like the James Webb Space Telescope pair coronagraphs with advanced algorithms that digitally subtract lingering glare, peeling back layer after layer of interference. The result, in 2022, Webb revealed Vega's debris disk in unprecedented detail, showing ripples and gaps that suggest unseen planets sculpting the dust. The real surprise came when scientists realized Vega isn't just hiding its surroundings, it's hiding itself. High-resolution spectroscopy revealed the star isn't perfectly round. It spins so fast its equator bulges outward, creating temperature variations that distort its light. Without coronagraphs to tame the glare, these subtleties would remain lost in the noise. Even Vega's poles, where magnetic fields concentrate, emit faint X-rays. A whisper of activity drowned out until specialized tools brought it into focus. What makes this star's story so compelling isn't just the tech used to study it, it's the reminder that brightness can be deceptive. The universe's most luminous objects often guard their secrets most fiercely, forcing us to invent new ways of seeing. And as coronagraphs evolve, who knows what else we'll uncover? Maybe planets tucked into Vega's glare or stellar pulsations too subtle to spot amid the radiance. One thing's certain, in astronomy, sometimes you have to block out the light to see the truth. At the edge of a distant galaxy cluster, a star's light takes a detour not by choice, but by the sheer warping power of gravity. This cosmic detour is no gentle bend. It's a full-fledged hall of mirrors where the star's image splinters into multiple arcs and smears across the sky like reflections in a broken funhouse mirror. Welcome to the world of gravitational lensing, where the universe itself becomes a magnifying glass, twisting and amplifying starlight in ways that baffle even seasoned astronomers. The phenomenon hinges on Einstein's revelation. Massive objects don't just pull on matter, they bend the fabric of space-time, altering the path of light itself. When a star aligns perfectly behind a galaxy cluster or black hole, its light doesn't travel in a straight line to us. Instead, it curves around the foreground mass, creating a bizarre optical illusion. Sometimes the star appears as duplicate images, a celestial doppelganger effect. Other times, its light stretches into an ethereal arc or even a complete ring, an Einstein ring, encircling the lensing object like a halo. The first time astronomers witnessed this, they thought their instruments were glitching. How could one star appear in 4 places at once? Take the famous Hamilton's object, for example. What looked like a pair of identical blue stars in a telescope's eyepiece turned out to be a single star's light split by the gravity of an intervening galaxy. The duplicates weren't just visual quirks, they arrived at Earth at slightly different times, thanks to the varied paths their light traveled. One image might show the star as it was 100 years ago, while another captures it decades later, a cosmic time machine disguised as a trick of gravity. But lensing does more than just duplicate stars, it amplifies them. A faint, faraway star that would normally be invisible to our telescopes can suddenly blaze into view when a massive object bends its light toward us. In 2018, astronomers spotted a star nicknamed Icarus, magnified over 2,000 times by a foreground galaxy cluster's gravitational field. Without this cosmic zoom lens, Icarus would have remained forever hidden in the void. The real challenge comes when lensing distorts stars beyond recognition. Some appear as warped streaks, their light smudged across the sky like wet paint. Others flicker unpredictably as passing dark matter clumps further twist their light's path. These distortions aren't just inconveniences, they're gold mines for science. By studying how lensed starlight bends, researchers can map the distribution of unseen mass in the universe, including elusive dark matter. Every distorted image is a clue, a fingerprint left by the invisible scaffolding of the cosmos. What's mesmerizing is how this stellar sleight of hand reveals the universe's layered complexity. A single twinkle in the night sky might not be a star at all, but a reflection of a reflection, a light echo warped by forces we're only beginning to understand. And as telescopes grow sharper, we're finding that these gravitational illusions aren't rare anomalies. They're everywhere, hiding in plain sight. The stars we think we see might just be ghosts, their true forms lying elsewhere, reshaped by the unseen hands of gravity. One night in 2015, astronomers watching the constellation Cygnus saw something impossible: a star named KIC 8462852, later nicknamed Boyajian star, dimmed by a staggering 22% in a matter of days. Stars don't just flicker like candles in the wind. They're massive, stable furnaces, their brightness changing glacially over millions of years. Yet here was a sun-like star, its light plunging erratically, as if something vast and unseen kept passing in front of it. The data defied every explanation: planets too large, a dust cloud too irregular, theories piled up, alien megastructures, a swarm of comets, even a rogue black hole. But the truth might be stranger than fiction. The leading suspect is a cosmic cataclysm rarely seen, a star swallowing its own planetary system. Imagine a young, turbulent star, its infancy marked by violent outbursts. As it settles into maturity, it begins ingesting the remnants of its chaotic birth. Planets shattered by gravitational tugs, moons ripped apart by tidal forces, or vast rings of debris spiraling inward. Each time one of these fragments approaches, it's torn into a cloud of dust and gas, temporarily veiling the star. The result: epic, unpredictable eclipses like a celestial beast consuming its young. But there's another possibility. Boyajian's star might have collided with an interstellar dust cloud, a rogue filament drifting through the galaxy's spiral arms. These clouds are normally diffuse, but if conditions are just right, if the star's magnetic field or stellar wind funnels dust into dense clumps, the obscuration could be dramatic enough to mimic a partial blackout. Even stranger, some simulations suggest the star could be surrounded by a massive, tilted disk of debris, warped by an unseen companion star. As the disk wobbles over centuries, it occasionally casts shadows deep enough to blot out a fifth of the star's light. The most tantalizing clue came in 2021, when follow-up observations revealed the star's dimming episodes weren't random. They clustered in time like seasons of cosmic weather. That pattern points to something cyclical, perhaps a family of shattered comets on elongated orbits, returning every few decades to cast their icy shadows. Or maybe the star itself is unstable, prone to fits of dimming as its outer layers convulse with magnetic storms far more violent than our sun's. What makes this mystery so compelling isn't just the star's bizarre behavior, it's the reminder of how much we still don't understand about stellar adolescence. Stars like this might be cosmic delinquents, their wild phases hiding clues to how planetary systems form and die. And somewhere out there, others like it could be fading in the darkness, their secrets written in the flickers we've yet to catch. Some galaxies are so dark they barely deserve the name, vast cosmic structures where stars are scattered like lonely embers in an endless night. These dark galaxies contain so few stars that their combined glow barely registers against the void, their presence betrayed only by the faintest whisper of starlight. Yet astronomers suspect they exist, hidden in plain sight, their true nature cloaked by the very darkness that defines them. The evidence: strange gravitational footprints in the cosmos, places where unseen mass tugs at the fabric of spacetime without the visible stars to account for it. Take the bizarre case of Dragonfly 44, a galaxy in the Coma cluster. At first glance, it seemed unremarkable, a smudge of light in a telescope's eyepiece. But when researchers measured its mass, the numbers didn't add up. The stars they could see accounted for less than 1% of the galaxy's total weight. The rest, an unseen halo of dark matter, its gravity holding the meager stars together like invisible glue. If dark galaxies have stars at all, they're so sparse that a traveler crossing one might see nothing but blackness for thousands of light years, their ship's hull bathed only in the cold glow of dark matter's faintest influence. Finding these shadowy realms requires tools beyond ordinary telescopes. Instead of hunting for starlight, astronomers map the hydrogen gas that often lingers in these galaxies, its radio waves piercing the darkness like a distant foghorn. Others track the subtle distortions of background starlight gravitational lensing caused by the galaxy's unseen mass. In 2016, a team using the ALMA radio telescope spotted a candidate dark galaxy near the Milky Way, its gas swirling in a telltale disk but with almost no stars to illuminate it. The discovery hinted at a universe teeming with these phantoms, their stars so isolated they might never know another sun's warmth. The most haunting possibility is that some dark galaxies could be cosmic fossils, remnants of the early universe where stars failed to ignite en masse. Picture a cloud of primordial gas that never quite collapsed into stellar nurseries, its potential frozen in time. If stars do smolder within them, they'd be ancient and faint, their light strained through eons of expansion. Telescopes like JWST might one day spot these survivors, their dim glow a testament to a universe that didn't just build galaxies of light, but also of shadows. What's humbling is realizing how much of the cosmos might slip past our gaze. For every glittering spiral like the Milky Way, there could be a dozen dark galaxies, their stars drifting unseen. They're reminders that the universe writes its stories not just in light, but in the invisible ink of gravity and time. And somewhere in those depths, stars burn alone, their light too faint to reach us, their existence known only by the silence between the shadows. Some stars don't just hide, they vanish in plain sight, erased by a cosmic spectacle so bright it rewrites the sky. Picture this, a supernova explodes, its light flooding telescopes with brilliance enough to outshine entire galaxies. But nestled in that blinding aftermath, something lingers, not the remnants of the dead star, but a survivor, a companion star that weathered the blast. This is the star behind the supernova's afterglow, its faint glow drowned in the radiance of destruction, like a firefly hovering near a forest fire. Take the case of supernova 1987A, one of the most studied stellar explosions in history. For decades, astronomers assumed the blue supergiant progenitor star had died alone. But as the supernova's light faded, infrared telescopes began picking up an anomaly, a persistent heat signature that shouldn't have been there, the leading theory. A binary companion, once orbiting the doomed star, had been scorched but not obliterated by the explosion. The supernova's shockwave would have stripped its outer layers, leaving behind a smoldering core, its light now competing with the fading echoes of its partner's death throes. Spotting such stars requires patience and precision. As the supernova's glow dims over years or even centuries, the hidden companion's light, once buried, begins to seep through. Instruments like the James Webb Space Telescope, with its unparalleled infrared sensitivity, can tease apart these subtle signals. By analyzing the spectrum of the lingering light, astronomers hunt for chemical fingerprints, unusual ratios of hydrogen or helium that betray the survivor's presence. It's like listening for a whisper in a thunderstorm, waiting for the noise to fade just enough to hear. The implications are profound. If these hidden stars exist, they could rewrite our understanding of supernova. Many massive stars, it turns out, live in binary systems. When one explodes, the companion might be flung away at incredible speeds, becoming a runaway star with a radioactive sheen. Others might remain bound to the supernova remnant, their orbits permanently altered by the violent loss of mass. Some could even be zombie stars, partially stripped of their outer layers but still burning, their surfaces scarred by the explosion's heat. But the real challenge isn't just finding these stars, it's unraveling their stories. Each survivor carries clues about the supernova itself, how asymmetric the explosion was, how much material was ejected, even the precise moment of detonation. In a way, they're cosmic witnesses, their very existence a testament to the chaos they endured. And as telescopes grow more powerful, we're not just searching for hidden stars, we're piecing together the final moments of their fallen partners, one flicker of light at a time. Deep in the cosmic shadows, a star might exist that emits no light at all, not a flicker of visible glow, not a whisper of radio waves, nothing. This isn't a black hole or a dead stellar remnant, but something far stranger, a star made of matter so exotic or shaped by conditions so extreme, it defies every wavelength we've ever used to study the skies. Imagine a celestial object that doesn't just hide behind dust or distance, but one that fundamentally rejects the very idea of visibility. The concept shatters conventional astronomy. Stars, by definition, are luminous balls of plasma, their nuclear furnaces radiating energy across the spectrum. But what if a star's physics worked differently? One hypothetical possibility involves strange stars, theoretical objects composed of quark matter, a dense, exotic state where protons and neutrons break down into their fundamental components. Under enough pressure, this quark soup could stabilize into an ultra-dense star that emits no photons, cooling rapidly into near invisibility. Or consider a star cloaked in a sheath of perfectly absorbing particles, a cosmic version of a blackbody that swallows all radiation before it escapes. Detecting such an object would require rethinking how we observe the universe. Without light to guide us, astronomers would need to rely on gravitational signatures, telltale tugs on nearby stars, or the subtle warping of space-time revealed by microlensing. A star like this might also betray its presence through rare interactions with interstellar gas. If it plows through a hydrogen cloud, the collision could generate shockwaves detectable in radio or X-rays, even if the star itself remains dark. The most tantalizing clues might come from anomalies in cosmic motion. If stars in a particular region orbit an invisible mass with no corresponding black hole or dark matter halo, we could be staring at the gravitational footprint of a truly invisible star. Projects like the Vera-Rubin Observatory, set to map billions of celestial objects, might spot these discrepancies by accident, a starless wobble in the fabric of space. What's thrilling isn't just the hunt for such an object, but what it would mean if we found one. A star that emits no light would challenge our foundational understanding of stellar physics, forcing us to rewrite textbooks on how matter behaves under extreme conditions. It might even hint at forms of energy or particles we've yet to discover, lurking in the darkness just beyond our perception. And that's the ultimate lesson of astronomy. Sometimes the most profound truths aren't written in the stars we see, but in the voids between them. Far beyond the crowded spirals of galaxies and the bustling star clusters lies the cosmic void, an expanse so empty, so devoid of matter, that a single star within it would shine like a lone lantern in an endless desert. These voids stretch hundreds of millions of light-years across, regions where galaxies are few and far between, and the space between them is a near-perfect vacuum. In such emptiness, a solitary star would be more than just rare. It would be a cosmic anomaly, a rebel against the universe's tendency to clump matter together. Isolated stars in these voids aren't just hard to find because of distance, they're nearly invisible by nature. Without nearby stars or nebulae to backlight them, their faint glow would dissolve into the darkness long before reaching our telescopes. Yet astronomers suspect these wanderers exist, stars flung from their home galaxies during violent collisions or ejected by the gravitational slingshot of a supermassive black hole. Some might even be primordial, drifting alone since the early universe, their light stretched and dimmed by eons of cosmic expansion. The few candidates we've detected hint at how extreme their isolation truly is. Take the star dubbed CXOJ 122518, 6 plus 144545, a blue giant found in the Boötes void, one of the largest known empty regions in the cosmos. This star shouldn't be there. Its brilliant, short-lived nature suggests it was born in a star-forming region, yet it drifts hundreds of light years from the nearest galaxy. The leading theory, it was hurled into the void by an ancient galactic collision, doomed to spend its brief, fiery life in utter solitude. What's haunting about these stars isn't just their loneliness, it's the silence. In the void, there's no interstellar medium to sculpt their stellar winds into glowing nebulae, no companion stars to ignite dramatic flares or eclipses. Their light travels unimpeded, with nothing to scatter or reflect it, making them ghosts even to the most sensitive instruments. Yet their very existence challenges our assumptions. If stars can survive and even form in these desolate stretches, what else might be lurking in the gaps we've written off as empty? Perhaps the most unsettling thought is this: for every star we've spotted in a void, there could be countless others too faint to see, their light stretched beyond detection by the universe's expansion. They burn unseen, their stories untold, their heat dissipating into the infinite cold. And in that emptiness, they rewrite the rules of what it means to be a star, not just a point of light, but a defiance of darkness itself. Buried deep in the petabyte-scale archives of astronomical surveys, hidden between the crisp signals of known stars and galaxies, there are cosmic phantoms waiting to be found, stars so faint or unusual that even our most sophisticated algorithms missed them. These aren't just dim dots in the void, they're misfits, outliers that defy categorization. A red dwarf might lurk undetected because its light blends into the glow of a brighter neighbor. A hypervelocity star flung from the Milky Way's core could be dismissed as noise in the data because its motion doesn't match expected patterns. Even pulsars, those precise cosmic lighthouses, sometimes slip through automated searches when their pulses are too erratic or their frequencies just outside the expected range. The challenge isn't just technical, it's a needle in a haystack problem on a galactic scale. Projects like the Sloan Digital Sky Survey have catalogued hundreds of millions of objects, while Gaia's precision astrometry tracks over 1 billion stars. But no algorithm is perfect. Subtle quirks, a star's unusual color index, a slight variability in brightness, or an odd spectroscopic signature can cause it to be flagged as an artifact or ignored entirely. Take the case of the zombie star in the Kepler dataset. Initially dismissed as instrument noise, it turned out to be a rare type of supernova survivor, its faint afterglow overlooked until a grad student manually reviewed the light curves. This is where citizen science steps in. Platforms like Zooniverse enlist thousands of volunteers to sift through data, their human eyes catching anomalies machines might miss. In 2021, participants in the Backyard Worlds project discovered a cluster of previously unnoticed brown dwarfs, some of the coldest ever recorded simply by scanning infrared images for tiny moving dots. There's even a term for these discoveries. Machines said no, humans said yes. The most famous example might be Tabby's star, whose bizarre dimming patterns were first flagged by amateur astronomers combing through Kepler's public data. The stakes are higher than just filling out star catalogs. Some of these overlooked objects could rewrite astrophysics. A star with an impossible metallicity might hint at ancient, unobserved supernova. A faint white dwarf drifting where none should exist could reveal long-forgotten galactic mergers. Then there's the tantalizing prospect of failed stars-brown dwarfs so cold they emit more heat in radio waves than light, or rogue planets masquerading as stars in low-resolution surveys. What's exhilarating is how democratic this hunt has become. With open-access datasets and user-friendly tools, anyone with an internet connection can uncover what supercomputers overlook. Projects like Planet Hunters and Disk Detective have led to peer-reviewed discoveries by amateur astronomers. proving that the next cosmic revelation might not come from a mountaintop observatory, but from a laptop on someone's kitchen table. The universe's hidden stars aren't just waiting in the darkness, they're buried in plain sight, camouflaged by the sheer volume of data we've collected. And sometimes all it takes to find them is a fresh pair of eyes. In the earliest moments of the cosmos, before galaxies took shape or planets even existed, the first stars blazed to life, and these primordial giants didn't play by the rules we know today. Born from clouds of pure hydrogen and helium, untouched by the heavier elements that fill modern stars, these celestial pioneers burned at temperatures and intensities that would make today's supergiants look like candle flames. Their lives were spectacularly brief, some surviving only a few million years before collapsing in violent explosions that seeded the universe with the first heavy elements. But what's astonishing isn't how they lived, it's how they vanished without a trace, leaving behind only whispers in the cosmic microwave background. These first-generation stars, dubbed Population 3 stars, were so massive, so unstable, that none are believed to survive today. Simulations suggest they ranged from 50 to 1,000 times the Sun's mass, their cores so hot they fused elements at breakneck speed. Unlike modern stars, they had no brakes, no carbon or oxygen to help regulate their nuclear reactions. The result, a runaway fusion process that consumed their fuel reserves in geological microseconds. When they died, many may have collapsed directly into black holes without the traditional supernova farewell, their light snuffed out like a candle in a vacuum. Yet their fingerprints linger. When the James Webb Space Telescope analyzed the spectra of distant quasars in 2023, it detected odd ratios of elements like carbon and iron patterns that only make sense if they were forged in the hearts of these ancient behemoths. Even more telling are the metal-poor stars found in the Milky Way's halo, relics from just one generation later that contain mere traces of heavier elements. These aging survivors act like cosmic archaeologists, preserving chemical clues about their long-dead ancestors. The most haunting legacy of Population 3 stars isn't in what we've found, it's in what we can't see. Their deaths triggered the cosmic dawn, flooding the early universe with enough ultraviolet radiation to strip electrons from hydrogen atoms in a process called reionization. That event left an indelible mark on the cosmic microwave background, the afterglow of the Big Bang. By studying subtle temperature variations in this radiation, astronomers have mapped where these stars likely clustered, their ghostly outlines visible only as faint distortions in the fabric of spacetime itself. What makes this hunt so profound is the realization that we're piecing together a history written in absence. The universe's first stars didn't leave behind dazzling nebulae or spinning pulsars, just a faint chemical echo and the shadow of their influence on everything that came after. They're the ultimate hidden stars, not just obscured by distance or dust, but erased by time itself. And yet, their legacy is everywhere in the iron in our blood, the silicon in our planet's crust, and the very fact that later stars could shine at all. They vanished so that everything else could begin. At the heart of the galaxy Messier 87, a cosmic monster lurks, a black hole so massive its shadow stretches wider than our entire solar system. When the Event Horizon Telescope captured its now iconic image in 2019, the world marveled at the glowing ring of light circling the abyss. But hidden in that very glow might be stars we've never seen, their light bent and swallowed by the black hole's immense gravity. The shadow itself acts like a cosmic cloak, a region where space-time curves so sharply that even photons can't escape. But just outside that edge, the forces are warping starlight in ways we're only beginning to understand. The challenge isn't just the black hole's darkness, it's the way its gravity distorts everything around it. Stars orbiting close enough would have their light stretched into unrecognizable smears, their images duplicated or twisted into Einstein rings by gravitational lensing. Some might appear to freeze in time, their light redshifted into near invisibility as they approach the event horizon. Others could be magnified briefly by the black hole's lensing effect, flaring into view before vanishing again behind the shadow's edge. It's like trying to spot fireflies near a floodlight, their faint glow drowned out by the brilliance of the accretion disk, yet astronomers aren't giving up. One promising approach involves studying the polarization of light around the black hole. The Event Horizon telescopes follow-up observations revealed intricate patterns in the magnetic fields near M87's core patterns that might betray the presence of hidden stars. As these stars orbit, their light interacts with the black hole's magnetized plasma, leaving subtle fingerprints in the polarized data. It's akin to reading ripples in a pond to deduce the shape of unseen stones beneath the surface. Another tactic leans on timing. Stars skirting the black hole's shadow would follow predictable orbits, their motions governed by relativity. By tracking slight variations in the accretion disk's brightness, tiny dips or flares that recur at regular intervals, researchers could infer an unseen star's presence, much like detecting an exoplanet by its transits. Already, teams have modeled how a star's gravity might perturb the disk's inner edge, creating spiral density waves visible in future high-resolution observations. The most tantalizing possibility, a star surviving where it shouldn't. Theory suggests that in the chaotic environment near a supermassive black hole, some stars might avoid being torn apart, instead settling into stable orbits just outside the event horizon. These S-stars, like those observed near our own Milky Way's central black hole, could endure for millennia, their light perpetually bent and magnified by the space-time whirlpool around them. Finding one in M87 would rewrite our understanding of extreme stellar endurance. What makes this hunt so exhilarating is the sheer audacity of the challenge. We're not just looking for stars hidden by distance or dust. We're trying to spot them near the universe's ultimate optical illusion, where gravity twists light into knots. Every flicker in the data, every anomaly in the glow, could be a clue pointing to stars dancing on the edge of oblivion. And with each new observation, we peel back another layer of the black hole's shadow, not just to map the darkness, but to find the light trapped within it. Beyond the Milky Way's sprawling arms, hidden in the faint glow of orbiting dwarf galaxies, lies an entire population of stars astronomers almost missed. These aren't the brilliant giants lighting up galactic centers, they're solitary wanderers drifting through the sparse outer halos of satellite galaxies like the Small Magellanic Cloud or Draco Dwarf. So dim and spread out, they vanish into the background of most telescopic surveys, their light drowned out by the brighter crowds of inner star clusters. Yet these overlooked stars hold secrets about galactic evolution that their flashy cousins can't reveal. Take the case of the Sculptor Dwarf Galaxy. When researchers first mapped its outer regions using the Dark Energy Camera in Chile, they expected to find emptiness. Instead, they discovered a sparse but significant scattering of ancient red giant stars so faint they emitted just 1/10,000th the light of a typical Milky Way star. These weren't just dim, they were relics formed over 10 billion years ago when the dwarf galaxy itself was young. Their chemical makeup told a startling story. Unlike stars in the sculptor's core, these halo stars contained almost no heavy elements, suggesting they formed from nearly pristine cosmic gas before supernova enriched their surroundings. The challenge in spotting such stars isn't just their faintness, it's their camouflage. Dwarf galaxy halos blend seamlessly with the Milky Way's own stellar halo, creating a cosmic Where's Waldo scenario. Advanced techniques like narrowband photometry help separate true members from interlopers by measuring subtle differences in metal content. The Pristine Survey, for instance, uses a specialized filter to detect the absence of metals in starlight, flagging ultra-metal poor stars that likely belong to these ancient halos. Every confirmed detection is like finding a needle in a galactic haystack. What makes these stars so scientifically precious is their isolation. unlike stars in crowded galactic cores, where collisions and gravitational interactions constantly reshape orbits, halo stars drift undisturbed, preserving traces of their host galaxy's earliest days. Their motions encode information about the dwarf galaxy's original size before tidal forces stripped away its outer layers. Some might even be stolen goods snatched from other dwarf galaxies during long-ago collisions. The Large Magellanic Cloud's halo, for example, shows stars with chemical signatures matching the nearby Small Magellanic Cloud, evidence of a gravitational tug-of-war playing out over billions of years. The Vera Rubin Observatory's upcoming legacy survey of space and time promises to revolutionize this hunt. By scanning the southern sky repeatedly over a decade, it'll catch the slight motions of these faint halo stars, distinguishing true residents from foreground Milky Way objects. Early test runs have already revealed previously unknown streams of stars linking dwarf galaxies to their halos like cosmic breadcrumbs marking paths through the darkness. These ghostly stellar populations force us to reconsider what defines a galaxy's boundaries. The visible edge of a dwarf galaxy isn't its true limit. The halo extends much farther, a tenuous web of stars clinging to their tiny galactic host. And in that dim glow, we read a story of survival, how the smallest galaxies in the universe cling to their stars against all odds, whispering their history in light we're just learning to see. Most stars drift through the cosmos at a leisurely pace, bound by gravity's gentle tug, but not this one. Clocking speeds over 1,000,000 miles per hour, this cosmic speedster isn't just fast, it's breaking free entirely. Hypervelocity stars are the universe's runaway trains, hurtling through intergalactic space so fast they'll never return to their home galaxies, their secret. A gravitational slingshot so violent, it flings them into the void like stones from a cosmic catapult. The most likely culprit, a dance with the monster at the Milky Way's heart. Picture a binary star system wandering too close to Sagittarius, a star, our galaxy's supermassive black hole. As the black hole's gravity rips the pair apart, one star gets captured into a tight orbit, while the other is flung outward at unimaginable speeds. It's nature's ultimate balance, for every action an equal and opposite reaction. The energy stolen by the captured star transforms its partner into a hypervelocity projectile, ejecting it fast enough to escape the galaxy's gravitational grip forever. Not all these speed demons come from black holes, though. Some might be survivors of galactic collisions, stars hurled into the abyss when their home galaxy tangled with another. Imagine the Large Magellanic Cloud smashing into the Milky Way billions of years ago. The gravitational chaos could have launched stars like pinballs, sending them careening into intergalactic space. Others could be exiles from dense star clusters, where close encounters with neighboring stars build up enough kinetic energy to kick a member out at hypervelocity speeds. Tracking these stars is like trying to photograph a bullet mid-flight. They move so fast that their positions shift noticeably in just a few years, their light stretched and dimmed by the Doppler effect as they race away. The first confirmed hypervelocity star, discovered in 2005, was speeding outward at nearly 2,000,000 miles per hour, so fast it will eventually leave the local group of galaxies entirely. New surveys like Gaia are now uncovering dozens more, each with trajectories tracing back to violent origins near the galactic center. What's astonishing isn't just their speed, it's where they're headed. Unlike most stars which orbit peacefully within galaxies, hypervelocity stars are intergalactic pioneers. Given enough time, they'll cross the gulf between galaxies entirely, their light fading into the darkness of the cosmic voids. Some might even carry planets with them, frozen worlds ripped from their native systems and condemned to an eternal journey through the cold. These stellar fugitives force us to rethink gravity's limits. They're proof that the universe can fling objects with forces beyond our everyday experience, etching their stories not in light but in motion. And somewhere out there, countless more are racing unseen, their paths scribbled across the cosmos in streaks we've yet to trace. Imagine a cosmic thread thinner than an atom yet stretching across the entire universe, a flaw in the fabric of space-time so dense, its gravity bends light like a funhouse mirror. This is the hypothetical cosmic string, a relic from the universe's earliest moments, predicted by theory but never observed. And if these bizarre structures exist, they could be hiding stars in plain sight, warping their light so severely that they vanish from our telescopes entirely. Cosmic strings are thought to have formed during the rapid cooling of the infant universe, when space-time itself underwent phase transitions, like cracks forming in ice as water freezes. These one-dimensional defects would carry unimaginable density, with a single inch of string weighing as much as Mount Everest. Their gravitational influence would be so extreme, they'd bend passing light into loops or even create double images of stars behind them. A star positioned just right or just wrong could have its light stretched, smeared, or redirected around the string like water flowing around a boulder, rendering it invisible to conventional observation. The most tantalizing possibility, a cosmic string acting as a natural cloaking device. Picture a star whose light gets wound around the string so tightly that its photons never reach us directly. Instead, they spiral endlessly along the string's gravitational field, trapped in an infinite loop. To Earth's telescopes, the star would simply disappear. Only indirect clues like gravitational microlensing events with no visible source or strange distortions in the light of background galaxies might hint at the string's presence and the star it's hiding. Even stranger cosmic strings could create ghost stars, optical illusions forged by their extreme gravity. A string passing between us and a distant star might split its light into multiple images, each appearing decades apart due to the varied path lengths around the string. Astronomers could observe what seems like a single star flickering in and out of existence, not realizing they're seeing the same object at different points in its timeline. The hunt for these hidden stars isn't just about curiosity. If cosmic strings exist, they'd be fossil evidence of the universe's first trillionth of a second, offering clues about physics far beyond what particle colliders can probe. And any stars they conceal would be cosmic prisoners, their light bent into submission by spacetime's most elusive defects. Until we detect the strings themselves, perhaps through their faint gravitational wave signatures or their telltale imprints on the cosmic microwave background, these stars will remain theoretical ghosts dancing behind the curtains of relativity itself. The universe is expanding faster than light can keep up, an unsettling truth that means entire galaxies and the stars within them are vanishing over the cosmic horizon, not just from our sight but from our reality. Every second, more stars slip beyond an invisible boundary where their light will never, under any circumstances, reach us. The photons they emit now travel toward an unreachable shore, like letters mailed to an address that no longer exists. These aren't just stars hidden by dust or distance, they're casualties of cosmology, erased from our future not by darkness, but by the relentless stretching of space itself. Consider the numbers. The observable universe spans about 93 billion light-years, containing an estimated 200 billion galaxies, but the entire universe. If inflation theory is correct, it could be at least 10 to the power of 23 times larger, a scale so vast that the stars within it outnumber every grain of sand on every beach Earth has ever known. And yet we'll never see them. Not because our telescopes aren't powerful enough, but because the space between us and those stars grows faster than light can bridge the gap. Their light races toward us, but the highway beneath it is stretching taut, turning their journey into a cosmic treadmill where they make progress without ever arriving. This isn't just about distance, it's about time. The universe's expansion accelerates, meaning stars born today in galaxies beyond our horizon will forever remain strangers. Their existence is a statistical certainty. The laws of physics don't change just because we can't see them. They'll live, burn, and die in isolation, their stories locked away in pockets of space-time we can't access. Some might harbor planets with civilizations gazing at their own night skies, equally unaware of our existence. The irony is crushing. The universe teems with more stars than we can fathom, yet the majority are destined to be eternal mysteries. What's haunting is how this reshapes the meaning of hidden. These stars aren't obscured by cosmic dust or tucked behind black holes. They're severed from us by the fundamental rules of reality. Even if we could travel at light speed, we'd never reach them. The space between us isn't just vast, it's growing faster than we can chase it. And so, the universe keeps its greatest secrets not behind veils of darkness, but behind the inexorable march of expansion, a curtain drawn faster than light can part it. Yet in that separation lies a strange comfort. The unknowable stars remind us that the cosmos is grander than our grasp, that wonder doesn't end where our vision does. They're the ultimate lesson in humility. The universe owes us nothing, not even the promise of being seen. And so we're left to ponder not just the stars we'll never find, but the ones that, by the laws of physics, will never find us. We've journeyed through the cosmos' best-kept secret stars cloaked in dust, phantom lights bending around black holes, dark matter giants glowing faintly with invisible energy. From hypervelocity runaways flung between galaxies to ancient population, 3 stars that vanished without a trace. Each of these 30 hidden wonders reveals just how much of the universe operates beyond our sight. They're not just cosmic oddities, they're proof that the night sky is an illusion, a flickering curtain hiding realities far stranger than we imagined. These elusive stars force us to rethink what it means to see. Some hide by nature, like quark stars so dense they swallow light. Others are victims of circumstance, orphaned in voids or drowned out by their own brilliance. And then there are those erased by time, their light stretched thin by expansion before it could ever reach us. But the most humbling truth, this is just the beginning. For every hidden star we've theorized, countless others likely exist. Their stories written in wavelengths we can't yet detect or tucked behind the universe's most extreme physics. So what's left to discover? Perhaps stars made of entirely new states of matter, or ones entangled with parallel universes. Maybe entire populations drifting in the voids, their light too faint for our telescopes. The universe doesn't hide its secrets out of spite, it's simply vaster than our tools can grasp. And that's the real magic. Every time we invent a new way to look, the cosmos reveals another layer of its brilliance. Now it's your turn. What celestial mystery captivates you? Drop your thoughts below. And if this journey through the unseen cosmos left you starstruck, don't forget to like, subscribe, and share. The universe is full of stories waiting to be told, and together we'll keep uncovering them, one hidden light at a time.